let's prove a couple of results about irrational numbers. The first result is from 500 BC, and it's the result that the square root of 2 is irrational. Attributed to Hippasus. The proof goes by contradiction. Assume that the square root of 2 is equal to a rational number p over q. Now we can square both sides. And see that 2q squared is equal to p squared. Now let's look at the prime factors, especially at the prime factors 2. Say 20 is equal to 2 to the 2 times 5, right? 4 times 5. And so there are two prime factors, 2 in 20. When we look at the prime factors here, because this is a square, there is an even number of prime factors 2. And because of the 2 here, we get an odd number of prime factors 2. And on the right-hand side, because it's a square, we have an even number of prime factors. Factors 2. And obviously this is a contradiction, showing that the initial assumption that the square root of 2 is rational does not work. This result is very important, and the Pythagoreans, which you see here, they were not pleased at all. There is a legend which says that Hippasus had to pay with his life for discovering this result. But then there were others like Theodorus, who was a teacher of Plato, and also Theaetetus, friends, and they eventually understood this and also saw that it applies for all other integers here which are not squares. So that's our first result. The next result deals with a concept which came much later, almost 2,000 years later. It is the concept of logarithms, which has been invented by John Napier and Joost Bürgi. Napier is an English mathematician, and Joost Bürgi is a Swiss mathematician. They found these logs independently. And let's just quickly review logs. We stick to the base 10 log. So if we take the, just write 10 here to the base so that it's more clear. So if we take 10,000 and we want to know what is the log to the base 10 of 10,000, we want to know which power of 10 gives us 10,000, and the power is equal to 4, and we see that this is, or the log 10 of 1 over 100 is minus 2, because 10 to the minus 2 is 1 over 100. So logarithms also produce a lot of irrational numbers, and the theorem which we are going to look at, just a prototype result, is that the log to the base 10 of 2 is irrational. It's exactly the same principle, and you can practice this with other numbers. The principle is to assume that we have p over q such that log of 10 based log of 2 is equal to p over q. But now we don't square, but we just invert the log. How do we invert the log? We take the power, we take both sides to the power 10. 10 to the power of this is just is equal to log 10 2 is equal to 2. And on the right hand side we have 10 to the p over q. So we see that it's still not clear. We have to also take the power q here. So we have 2 to the q is equal to 10 to the p. I think now it's more clear because we have all integers on both sides, right? But you see that if you look at the prime factorization here, there is no 5 which appears. There's a factor 5 here, has a factor 5. But this doesn't have a factor, has no factor, factor 5. And so that's a contradiction showing that the original assumption is not possible. These proofs need the fundamental theorem of arithmetic, which tells that there is a unique prime factorization of integers. There is another proof which I show in the slides, which is geometric, not for the log, but for the square root of 2 proof. And there one can just do it without the prime factorization using a descent argument, which is pretty beautiful and probably could have been the argument which the Pythagoreans found. Maybe a good starting point is Hilbert. Hilbert asked in 1900, Hilbert asked whether e to the pi irrational. Is this irrational? This is now called the Gelfond number. So let's just abbreviate it with G. So it's the Gelfond number. The reason why it's a Gelfond number because Gelfond proved that this is really irrational. But let's just rewrite this a little bit so you see that there is a kind of an attack. So if you have e to the pi, and if you would have e to the pi I, if you know complex numbers, e to the pi I is -1. That's kind of often considered the most important or most beautiful identity in mathematics because it combines e, pi, I, 1, and 0. And so e to the pi I is equal to -1. And so if we take, how can we write this? If you take this -1, if you take -1 to the power minus I, you see if you take -1 to the power minus I, you get e to the pi I to the power minus I, which is e to the pi minus I squared, which is e to the pi, which is just g. So that's just another way to write this beautiful Gelfond number. It would go too far to prove this, that this is irrational. It was the seventh, one of the seventh Hilbert's problem, which is an indication that it's a difficult thing. But let's just look at something else which is related to this. So remember, -1 to the minus I is equal to the Gelfond number. Let's just look at another number. Maybe let me leave this here and kind of look at another number, which I call the I for an I number, my favorite number. I for an I number, which is I to the I. I to the I. What's I to the I? I to the I is e to the I pi half. That's I. That's another way to write I. Here is I in the complex plane. Pi half is the angle. E to the angle. E to the I times the angle gives us the complex number. So this is another way to write this. And so if you take I to the I, we get e to the minus pi half, which is 1 over e to the pi half, which is 1 over the square root of e to the pi, which is 1 over the square root of this Gelfond number. So we see this I for an I number is actually just 1 over the square root of the Gelfond number. And if this would be P over Q, this would mean that 1 over G is equal to P square over Q square, which means G is equal to Q square over P square, which is not possible. So what we have just proven is that this I over I is irrational. Pretty cool. That's already the third part. It's getting more and more difficult. Let me just, you have covered that, you can turn off if you like. So the next thing is actually a lot of fun. I learned this, the next theorem I learned as a student from a computer scientist, because I have also taken a lot of computer science courses, also C8 in computer science course, and Gerhard Jäger showed this once. That was pretty cool. It's the following result, which that's number 4. But the question is there a pair of irrational numbers x and y such that x to the power y is rational. And the answer is yes. And it's not maybe the result, but it's the proof, which is totally amazing. So assume, let's look at the following number. It's square root 2 over square root 2, which is also called the Gelfond-Schneider number, square root 2 to the power square root 2. Now there are two possibilities. Either square root 2 to the power square root 2 is rational. So we can ask the following thing. Is it rational? If yes, if it is yes, then we have solved the problem. Because we can take x is equal to square root 2, which we have shown, this Hippasus result, that it's irrational. Another y is also irrational, and so this is also irrational. If not, then we take this as our x, and we take y is equal to square root 2. They are both irrational, so because we have just answered that square root 2 over square root 2 is irrational, so then this is irrational and this is irrational, and x to the y is square root 2 to the power square root 2 to the power square root 2, which is square root 2 to the square root 2 squared, which is square root 2 to the 2, which is 2, which is rational. So whatever happens, whether this is rational or not, we have established an example. By the way, this is known to be irrational. It's also called the Gelfond-Schneider number, honoring again these two mathematicians who independently found the solution to the Hilbert problem. 7. So this is a little bit of magic. There is something which is a little bit more involved even. Let me just mention it because it's so much fun, but it's more difficult. It's actually a whole article. I'm trying to just summarize in 1 minute an article. It's not so difficult, maybe two pages. But let me just explain quickly. So the question was, is it true that there exists a irrational x such that x to the power x is rational? Question. Is there x such that x to the x, so irrational, such that x to the x is rational? So the answer is yes. Yes, there is. And let me just explain this briefly. So if we look at the function x to the x, which is a pretty cool function, which is monotone. This is the function. This is x, and this is f of x, which is x to the x. So we see here the graph of this function. It's monotone from some point on. I think 1 over e is the smallest. But we can take, let's assume we take it from 1, and then 1 to the 1 is 1. So it's a monotone function here. And the question is, we want to find a x here which is irrational such that this is rational. It's not so obvious that this exists, because for the square function, for example, this doesn't work. I mean, x is rational even only if x squared is rational. But here, it is possible. And the thing is, what one has to analyze is just the places where this is rational and this is rational. So if you take here x is equal to p over q, and then this is rational a over b here. So we want to find this, we want to avoid these cases here. And if you write this down, what this actually means, so we have p over q to the power p over q is a over b. And then we take the q's power on both sides. So we have p over q to the power p is a over b to the power q. Now we can make an equation which doesn't involve fractions anymore by taking everything over. So we have p to the p times p to the q is a to the q, q to the p. So this is the equation which involves now integers p, q, a, b. And what one can show is that now this forces, just by looking at prime factors, one can show here, there's a little lemma here, that it means that q is equal to 1 and p is equal and b is equal to 1. Which means that this is only possible for integers. So these points can only be rational here if they are actually integer points. And now what one has to do is just take a rational here, which is not an integer, like maybe 7/5, and go back. And then it cannot be a rational number here. So you have to have an irrational number here, which is mapped into that. Pretty cool. And just uses the property of this function x to the x. Good. So the last part is maybe the most difficult part. By the way, I mean, I just should mention there are many open problems. This is a whole field of mathematics called transcendental number theory, and it's full of open problems. For example, one has no clue at all what happens when you take p to the e. So p to the e, for example, p to the e, nobody knows whether this is rational or irrational. Most likely it's irrational, but nobody knows. Also related to that, one has no idea about things like this. You know, you take pi to the pi to the pi to the pi to the pi. These are such large numbers that you cannot even check whether they are integers or not. Such examples have appeared. I heard this in a problem collection, in a Russian problem collection. And I mean, if you punch it into Mathematica, also that there's no way, the computer could not even store that number. And so computer scientists are strictly speaking often finitists or ultra-finitists, in the sense that they don't even accept these numbers before you can really realize them in the computer. So let's look at the last thing, which is the theorem that pi is irrational. Pretty important theorem. It has first been found by Jonathan Lambert, a Swiss mathematician, and the proof which I'm going to present is by Ivan Neven. So here, you see him here. Pretty cool proof. Not so easy, it needs a little bit time to digest. But let me try to explain his proof. So the proof is the following. Again, it's by contradiction. We assume that pi is equal to p over q. And now we take a large integer n. We just then will see that for large n this will have a contradiction, and then we look at the function f of x. F of x is equal to x to the n, and then we take p minus q x to the n, and then we divide by n factorial. So this is a polynomial, and you see, if x is equal to p over q, when x is equal to pi, that's 0, and if x is equal to 0, then it's 0. So this function looks, maybe I just draw this function here. Actually, I have it here on this tablet. That's the graph of this function plotted for n equal to 5. But let me just draw that quickly here so I can explain. So we have that function. This positive. It is actually, if you look at it, it's pretty flat here. Then it goes up, and then it's again flat, and then it becomes negative here. So this is 0, and this is pi, which is equal to p over q. So this is the function f of x. Now there's a little bit of physics coming in. The harmonic oscillator. So we look at this equation, f2 prime plus f is equal to f. So what is this? This is a forced harmonic oscillator. You think about this as a force driving, additional force, external force, driving this oscillator. And you learn in linear algebra how to solve this. So this is a harmonic oscillator. You learn how to solve this using You see, you have d squared plus 1, f is equal to small f, and now you just have to invert d squared plus 1, and so you see that f is equal to 1 minus d squared plus d to the 4th minus d to the 6th, etc. Of no, capital F is that f. So you see that f can be written like that, f, and then minus the second derivative of f, and then plus the fourth derivative of f, minus the sixth derivative of f. So this is the solution of this harmonic oscillator. Now what is very important is that f of 0 and f of pi are integers. Why is this the case? So you have to look at this at 0. You see actually that f is 0 here at 0, the second derivative is 0, and you see kind of if you take derivatives of that, and if n is getting so large that you have no more 0, then it has killed this n factorial, so that you only deal with integers. And similar for pi, this is completely symmetric, this with respect to pi. So these are both integers. And now you check something else. You check that f prime sinus x minus f times cosine x. Take the derivative of that. What you get is actually just f times sinus x. Why is this the case? This you can quickly check by just taking the derivative using the product rule. This is f2 prime sinus x. You have also here plus f times sinus x, which is by the definition just f times sinus x. And then you have a term which cancels, which is f prime cosine x, and here f prime cosine x, this cancels. And so you see this identity holds. Now this is pretty cool, because now we can use the fundamental theorem of calculus. We can integrate here from 0 to pi dx. This integrate here from 0 to pi dx. What happens? So if you look at that by the fundamental theorem of calculus, this evaluated at x equal to pi minus evaluated at x equal to 0. This part goes to 0. This part gives us just f of pi minus f of 0. But what we have here is, so this is an integer, which is positive. Positive integer is equal to this integral from 0 to pi f times sinus x dx. And notice that this is bigger than 0 here inside. So this cannot be 0. It has to be an integer bigger than 0. On the other hand, if you look at f times sinus x, if you look at this function here, this f times sinus x is smaller than equal than pi. That's the biggest x which you can do. It's smaller than pi to the n, and then you take here just p to the n, and then you divide by n factorial. So you see that this grows slower than the n factorial. This actually goes to 0 for n going to infinity. So for n going to infinity, this part goes to 0. But that contradicts the fact that it has to be an integer which is bigger than 0. And this contradiction shows that the initial assumption pi is equal to p over q is not possible. And so this proves this beautiful theorem of Lambert that pi cannot be written as a fraction p over q.